So let's continue talking about graphs and graph theory. So any questions from last time, which was like a long time ago, but we were talking about graphs, what graphs are. We were working through representations of graphs with adjacency matrices and incidence matrices. And I think we ended by talking about isomorphisms of graphs. So looking at when two graphs were the same. And the basic idea was simply renaming vertices. So if we have a graph like this, and we have a graph like this, right, we know that those are basically the same graph because the position on the paper doesn't matter. And if we were to flip this thing around, we could redraw it like this. And then it looks like this original graph, right? So how do we turn this original graph into this new one? We make a mapping of vertices. So we take vertex A to E, B to F, C to H, and D to G. And our requirement is that this is bijective. So remember what bijective means. It means it's both injective and surjective. So what does injective mean for a function or a map? Your own definition. Or what is not injective? So is that injective? All right, we have different points over here going to different points over here. As soon as I do this, as soon as I have 2 points going to the same place over here, it's no longer injective. So injective is also one-to-one. It means that everything over here maps to something unique over there. Okay, different points map to different values. So that's injective. Surjective means that every point over here has to have some arrow pointing to it, right, coming from somewhere. And if there's some point here that's not mapped to, then it's not surjective. So in terms of vertices, this means that you can't have two vertices mapping to the same vertex over there, right, which makes sense because otherwise you'd have fewer vertices on this side. And surjective means that every vertex here must be associated with some vertex in your original graph. So it's a one-to-one correspondence, basically. And if you can find this one-to-one correspondence that preserves adjacency, then we have an isomorphism. So over here, A and B are adjacent. That means that in our other graph, E and F should be adjacent, which they are. B and D are adjacent over here, which means that F and G should be adjacent, which they are, and so on. So we'd like to be able to look at two graphs and know if they're isomorphic or not, and it's a hard problem in general. But we can use what are called invariants. To help us know when things are not isomorphic. So what are invariants? Things that don't change under isomorphism. So for example, the physical location of two vertices might change between one graph and an isomorphic version of it, right? Here, everything that is adjacent to one another forms a square. Here it doesn't. Here we have edges crossing, here we don't. But those don't mean that the graphs aren't isomorphic. Okay, they're things that can change from one form to another. But here are some invariants. Our two main invariants, number of vertices and the number of edges. Those have got to be the same. And if you work through the definition of this bijective map, right, that'll convince you the number of vertices have to be the same, because injectivity and surjectivity give you that. And number of edges, if you think about the fact that this mapping must preserve adjacency, then you've got to have an edge over here for every edge over there. Right, so these are invariants. Another invariant is the collection of degrees. So if you look at the degree of each vertex, and I'm not calling it a set because it might have duplicates, but if you look at the degree of each vertex in one graph, and let's say you have vertices of degrees 2, 3, 4, 4, and 6, then in an isomorphic graph you've got to have the same set of degrees. Right? Isomorphism should not change the degree of each vertex, and that corresponds from preserving adjacency. So one thing we can do if we have two graphs is count the number of vertices. Different number of vertices, they're not isomorphic. Right? Count the number of edges. 4 edges, 5 edges, they're not isomorphic. Well, here's a graph with 5 edges, here's a graph with 5 edges. But that's not enough to say they are isomorphic. Right? If they have a different number of edges or vertices, we can say they're not the same. But just because they agree in the number of vertices and edges doesn't mean they're the same. And in this case, if we count vertices, we'll see that they're different. But we could find graphs with the same number of vertices that are not isomorphic. And the same with the collection of degrees. So it's generally a hard question, and it gets into some of these very hard questions that we talked about at the end of Wednesday. Okay, so let's talk about paths. So there's a graph, 5 vertices and several edges. So in general, when we talk about a path from one vertex to another, we mean kind of what you would think of intuitively. Suppose we want to start here and we want to end here. Okay, this is an example of a path. I'm going to label this S and E for start and end. So there's a path from the starting vertex to the ending vertex. This is also a path from the start to the end. And this is also a path from the start to the end. And we can make a very formal definition of what it means to be a path, but you've got the intuitive idea, right? Start at one point, and basically you can follow edges that are connected to whatever vertex you're sitting at. So if I try to start from here and jump up to here and then come down here, that's not a path, right? Because there's no edge connecting this to this. But if I go through that vertex, that's legal. So there's some ambiguity in terminology, but I'll try to make it clear when it comes up. So a simple path only uses an edge once. So here's a really weird path from S to E. Boing, 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 boing. Okay, but I'm going to call that not a simple path. It's technically a path because we're only using edges. When we get to a vertex, we're only traveling along an edge connected to it, right? But we're traveling along an edge more than once, so that makes it non-simple. All right, the length of a path is just the number of edges involved. So sort of the obvious notion from here to here, this is a path of length 1. Following this is a path of length 2. Following this is a path of length 3. All right, and finally a circuit is a path that starts and ends at the same vertex. And I've been, yes?
Question about length. You said it's the number of edges involved, but if you have a non-simple path, does it count that?
I think if it's non-simple, we'll count it multiple times. So, maybe with multiplicity. We usually aren't too interested in non-simple paths, so. All right, so these have all been undirected paths. We can also have directed paths, which is where we have a directed graph. And a directed path would need to follow the edges in the direction that they point. Okay, so sort of the obvious extension to having directions. So we can make a better definition of a connected graph. So a graph is connected if there exists a path between any pair of vertices. And I'm thinking undirected graph here. So 2 points, if there's a way to get from one point to another in all cases, then it's connected. Unconnected graph would be something like this. Right, and there's no path from A to D. So, an Euler path is a simple path containing every edge. And an Euler circuit is an Euler path that's also a circuit. So, is there an Euler path through this graph? Is there a simple path that contains every edge? There's bunches of them, right? So for example, we could start from vertex A, go to B, go to C, go to D, go to E, go back to C, and go back to A. And we've only used each edge at most once, Bless you. But we've found a path that contains every edge. And in fact, that's also an Euler circuit because we started and ended at the same vertex. So that has an Euler path and an Euler circuit.
Is that an Euler?
Say what?
Is that Euler or
Euler, E-U-L-E-R. That's a single edge. All right, so how about this graph? Is there an Euler path through here? Doesn't look like it. Right, and kind of no matter what you try to do, you seem to get stuck in the corners at some point. Right, and you can try this on your own, but it's pretty hard to envision a way to hit every edge. We can start in the middle and do that, and then we can come up here and we can get that, but we can't really go anywhere from here because we've used all the edges coming out of that vertex. So this one has no Euler path, and so it also has no Euler circuit. The circuit's also a path. All right, so here's a third one. So what about this? Is there an Euler path? All right, so what's your path going to be? Where do you want to start?
A to B, and then C to A, B.
Wait, so A to B,
Yeah,
and then,
B to C.
okay.
And then C to A,
Mm-hmm.
and then B to B,
Mm-hmm.
and then B to C. And then C to E, and then E to B.
Cool. Look good?
I from the that was just like this.
Awesome.
Oh,
But it's not a circuit, right? But it is a path. Perfectly valid Euler path. Do you think there's a circuit?
What is a circuit, but not an Euler?
An Euler circuit, yeah. So it turns out there's no Euler circuit for this, but there is an Euler path. All right, so there's a theorem. Worked out by Euler, go figure. So a graph has an Euler path. If and only if there are exactly 2 or 0 vertices with odd degree. So if we look at the degree of vertices, this was 2, 2, 4, 2, 2, no vertices of odd degree. And this turned out to have an Euler path and an Euler circuit. Over here, 3, 3, 3, 3, 4, 4 vertices of odd degree, no Euler path, no Euler circuit. Over here, 3, 2, 4, 3, 2, 2 vertices of odd degree, Euler path, no Euler circuit. So there's a second piece to this. it has an Euler circuit. If and only if there are no vertices with odd degree. So you can count up the degree of each vertex. If all the vertices have even degree, then you have an Euler circuit, which is also an Euler path. If exactly 2 vertices have odd degree, then you'll have an Euler path but no circuit. Otherwise, no path, no circuit. And you can probably convince yourself of this if you play with it for a while. Because what's kind of happening as you start drawing graphs, well, there's a graph, 2 vertices of odd degree, and we have a path, right? So let's just think about paths for now. If I want to add another edge, and this has to be a connected graph, otherwise there's points I can never reach. If I add another edge, wherever I add it, the degree of that vertex is now going to be even. And where this ends, if it ends on a vertex that has even degree, it's going to become odd. This is hard to explain in words. Play around with it though. Right, so so I've got odd, even, odd. If I add another edge, this is going to become even, right? And this will become odd. If I decide to connect this back here, this will become even, and this will become odd, right? As long as I'm drawing a path, right, I'm going to start where I left off, which had an odd degree, so it's going to become even. And I've got this stray vertex of degree 1, or I can put it on another vertex that already exists, which will make that vertex odd, right? But if I have more than 2 vertices with odd degree, basically you got to start at a vertex with odd degree, and you got to end at a vertex with odd degree. All right, that's a really weak hand wavy explanation, but play around with it, ask questions about it. But the trick is, if you have a graph, start at an odd degree, and you almost can't go wrong, right? And if you have a circuit, you can start pretty much anywhere, and you really can't go wrong. Because every time you get to a vertex, when you come in, you're going to have a way out, right? And if you come in 5 times and you go out 5 times, you've used up 10 worth of degree, right? If it's got more edges, you'll have a way to come back in, but since it's got an even degree, you'll also have a way to come back out. So you could spin an inductive proof from this. So that's a nice rule for dealing with Euler paths and Euler circuits. It's not so nice for Hamilton paths and Hamilton circuits. So a Hamilton path contains every vertex. Right, so it's a simple path that hits every vertex. And a Hamilton circuit is a Hamilton path. It's also a circuit. So this one, we can start here. We can go over. So that's got a Hamilton path.
Is that the say it contains every vertex once?
Good question. Yes. So here we can certainly find a path that contains every vertex. If we start here, we can come over, diagonal, over, and up. So that has a Hamilton path, but it's not going to have a Hamilton circuit.
Would you not go up though, because you already went to that vertex?
You want to travel each edge once. Yeah, you don't have to go up at all, actually. You can stop right here, you're right. But we can't find a Hamilton circuit for this. And the problem seems to be this stray vertex hanging off here at the edge, at the end of this edge. Because if we start here, we're going to travel along this edge, and that's it. We can't ever come back along that edge because it won't be simple. So there's no way to get back here. And if we start anywhere else, at some point, we have to come along here to get to this vertex, but since we didn't start there, we've got to get back to one of these other vertices, and the only way back from here is on that edge that we just traveled. So it looks like there's no Hamilton circuit here, even though there is a Hamilton path. And here's one where we don't have either. And it's kind of the same thing, but exacerbated by 3 of these dangling vertices, and there's no simple path that hits every vertex exactly once. And there's no known equivalent to Euler's theorems for when there is or is not a Hamilton path or a circuit through a graph. It's generally a complex problem. And it gets into this realm of these very complex problems that we touched on Wednesday called NP, complete problems. They're equivalent to Battleship and all of these other games. So let me show you something we can do with Hamiltons. I'm going to draw a funny looking graph. So there's a graph, 8 vertices and 12 edges. And I'm going to label these vertices as follows. I'm labeling with these funny binary codes. And I'm really just using these binary numbers as x, y, z coordinates. And that's a good right-handed coordinate system. And I'd like to find a Hamilton path through this graph, starting with 0, 0, 0. And that's not too hard to do. There's a Hamilton path, and in fact I can make it a circuit. And so I've found a simple path that hits each vertex exactly once and comes back to the original vertex. Okay, here's what's interesting about this. The way that this graph is drawn out, if we think of this as three-dimensional, and these are x, y, z coordinates, when we move from one vertex to an adjacent vertex, how many of the bits can possibly change? Exactly one, right? Because we're really moving through a coordinate system, and when we move along an edge, we're changing exactly one of our coordinates. So from here to here, the x-coordinate changes from 1 to 0. From here to here, the y-coordinate changes from 0 to 1, and so on. So if we follow this Hamilton path, we know two things. One, we're going to hit every possible bit pattern exactly once. And two, as we move from one bit pattern to the next, exactly one bit will change. So if we write out the 3-bit patterns corresponding to this path, what do we have?
Oh, dear.
Yeah. So what is that called? Do you remember? Say again? This is a gray code, yeah. So this is called a reflective gray code. And it's the code we use when we're building state machines and we don't want to have glitches. When we want to know that when we move from one state to the next, at most one bit is going to change. So it's a different way to count that avoids the glitches we get, for example, when we use traditional binary and we count from 3 to 4, and depending on when each of these bits change, we might get intermediate values like 2 or 7 and things like that. And so this comes out of an analysis of Hamilton paths. So that's kind of cool. All right, so let's do something genuinely useful. Not that that stuff's not useful. So I want to talk about something called Dijkstra's algorithm. This is the last thing we're going to do in graphs. Dijkstra was a computer scientist in the 50s, I believe. And studied graph theory, among other things. And this is related to the question of finding shortest paths through a graph. So if we have a graph where we have weights associated with each edge, yeah. If we have weights associated with each edge, we can define a weighted length of a path, not just the number of edges, but the sum of the weights of each edge from start to end. And we can ask what's the shortest weighted path from one point to another. So Dijkstra's algorithm is an efficient way, given a weighted graph with positive weights, to find the shortest path from one point to another. And it's kind of a quirky algorithm, but let's work with a sample graph. And let's say we want to find a path from A to F. And I'm going to put weights on here. And so you can start trying some sample paths. So if we just take a straight route up here, this is going to be 4 and 5 is 9, 6 is 15. If we take a path along the bottom, 2 and 10 is 12, and 3 is 15. Those seem the same. And if we come along here, 2 and 8 is 10 and 6 is 16, that's longer. But if we were to go 4 and 5 is 9 and then come down here, 2 is 11 and 3 is 14, that's shorter. Even though it had more edges, the total weighted length was smaller. And so we can ask what's the or a shortest path from, in this case, A to F. Bless you. And there's a nice deterministic algorithm we can use to answer this. So let me describe the steps, and then we'll go through it with this, and then we'll play with some other graphs and get some practice with this. So here's the basic algorithm. So mark your current node. That's the node you're starting with originally. So add tentative distances. A tentative distance is we can get here and at least this, at most this length. We might be able to find a shorter path, but we know if we travel this distance, we can get to this node. Okay, so it's a possible shortest distance. We know that we can get there in that distance, but we might be able to do better. And then we're going to do the mysterious step, which is relax adjacent nodes. And then mark the current node as visited. And mark closest node as current. And we'll go back up here. Okay, so let me do some steps to explain what this means. So we're going to start off with a current node of A. So I'm going to underline that. And I'm going to write down tentative distances before we've done everything. Well, we know that we can get to any vertex in an infinite number of steps. So our initial tentative distance everywhere is infinity. And hopefully we're going to do better than that. Okay, our initial distance to A is 0 because that's where we're starting from. Okay, so we mark the current node. That means I'm underlining it in red. I'm going to do tentative distances in blue. And then relax adjacent nodes. So what this means is we're currently working on node A. We know we can get to node A in a distance of 0. If we can get to node A in a distance of 0, and the distance from A to B is 4, we know that we can reach node B in 0 plus 4, which is 4 steps, right? Is 4 better than infinity? Yeah. So we're going to change this to be a 4. We also know since we can get to A in 0 and from A to C is only 2, we can get from A to C in a distance of 2, which is also better than infinity. So we're going to relax the distance to this node. We're just going to replace it with something smaller. Okay, now I'm going to mark the current node as visited, so I'm going to put a box around it and say we're done dealing with node A. And now I find the closest node, and I mark that as my current node. Well, all of these nodes have tentative distances of infinity. This has a distance of 2, 4. C is my closest node. So C is going to be my new current node, so I'm going to underline that. And now I'm going to relax adjacent nodes. Well, I can get to C in a distance of 2, and from there it takes 10 to get to E. That means I can get to E in 12. I may be able to do better. But since I know I can get here in 2, and this takes 10, I can definitely get to E in 12. And that's better than infinity, so I'm going to relax that to 12. Similarly, 2 plus 8 is 10, worst case to get to D. That's better. I'm going to relax that to a 10. 2 plus 1 means I can get to B in a distance of 3. That's better than my previous best distance of 4, so I'm going to relax that node also. And now I'm going to say my worst case distance to B is 3. Okay, I'm done relaxing the nodes. I'm going to mark what was my current node, which was C, as visited. And now I'm going to find the closest node and make that my current node. So what's my closest node now? Right, that's B. And we just keep iterating. So B is my closest node. Let's relax distances. So I can get to B in 3. I can take us 5 steps and get to D, and a total of 3 plus 5 is 8. That's better than 10. Let's relax this. And that's the only unvisited node I can get to from B is D. So that's my one step in my relaxation phase. Now I mark the current node as visited. And I find the closest node and make that my current. So I've got an 8, 12, and infinity. 8 is the closest, so this is my current node. Update the tentative distances. So 8 and 6 is 14. That's better than infinity. 8 and 2 is 10. That's better than 12, so I'll relax that to a 10. And those are my only edges to vertices that I haven't visited yet. Right? I don't need to come back here because I've already visited those nodes. So mark the current node as visited. Find the closest node, make that your current. Well, I've got a 10 and a 14. 10 is my closest node, so that's my current. And now, relax adjacent nodes. So 10 plus 3 is 13. That's better than 14. So I'll relax that node. And again, that's the only node that we can visit. So mark that as visited. And now take the closest node. Well, that's F. And there's nothing to relax from there. But in fact, since we're trying to get to F, as soon as we reach F, we're immediately done. And so our shortest path to F is actually 13. All right, so let's do that again with a little more housekeeping. All right, and again, we're going from A to F. And our initial distances are infinity. We're starting at A, that's our initial node, and the distance to there is 0. All right, so relax the nodes. So from A, we can get here in a distance of 2. And I'm going to record the path. Okay, the path to A is just A. So I'm going to write down the path to A, followed by this node. I don't have to add this node, I'm going to do it anyway. Followed by this node, C. So that tells me the path from A to C has a distance of 2. That's so far my shortest path to this node. 0 plus 4 is 4. That's better than infinity, so let's relax that to a 4. and the path is the path to A followed by this node B. So the only difference this time through is I'm recording these paths as we go. All right, so find the closest node. That's a 2. That's node C. That's going to be our current node. Let's relax from C. So C is a distance of 2 plus 10 is 12. That's a better distance than infinity. So this is 12. And how do we get to here? Take the path to C, which is AC. Then I'm just going to add this node E. Okay, 2 plus 8 is 10. That's better than infinity. So we'll make this a distance of 10. And the path is, again, AC followed by D. And 2 plus 1 is 3. That's better than 4. So we'll relax the distance to 3, and the path is the path to C, which is AC, followed by this vertex B. But now we're capturing the way that we get to these minimum distances. We can get here with a distance of 3 by going from A to C to B. We can get here with a distance of 10 by going from A to C to D, and so on. So the only thing we've added is we're keeping track of these paths. All right, so we're done with node C. We were done with node A in the beginning too. So find the closest node. We've got a 3, a 12, a 10, and an infinity. So 3 is closest, so relax from here. So 3 plus 5 is 8. That's better than 10, so let's get rid of this. Put down the new distance of 8. And the path is the path to B, which is ACB, followed by this vertex D. And that's the only thing we can relax from B. So we're done with B. And now we have an 8, a 12, and an infinity. So 8's our closest, so we're going to mark this as our current node. And relax from there. 8 and 6 is 14. And the path is the path to D, A, C, B, D, followed by this vertex F. 8 and 2 is 10, that's better than 12. So relax the distance to 10, and the path is A, C, B, D, followed by E. And that's all we can relax. So mark D. And now find new tentative distances. So 8, find the closest node. So we got a 10 and a 14, so this is the closest node. So relax from there. And 10 and 3 is 13, that's better. So mark this distance as 13, and the path is the path to E, A, C, B, D, E, followed by this vertex. And that's the only node we can relax. And now find the shortest, closest node, which is F. And there's nothing to relax from there because we visited all the other vertices, so mark that as done. And we're finished. So basically, as soon as we mark a node as having been visited, we have the shortest path to that node. Right, so since we're trying to get to F, it came out at the very end, but if we were trying to find the shortest path to D, we could have stopped right here and said the shortest path is from A to C to B to D. So here's our shortest path from A to F. A, C, B, D, E, F, and a distance of 13. Yeah.
Navigation works. Like,
Largely, yeah. I've had students who, for their SLP, were coming up with like optimal paths from building to building on campus and used Dijkstra's algorithm underneath. It's a pretty straightforward algorithm to code. There's a lot of technical details, of course, but the operations are pretty straightforward and it's pretty simple. I mean, it's really 4 or 5 steps just in a big loop. Keeping track of this stuff is just making some data structures to represent the pieces of your graph, storing the graph as an adjacency matrix or an adjacency list or something, in a way that lets you do things like say, okay, so from here, which nodes are adjacent, right? And an adjacency matrix, adjacency list gives you that automatically. Adding some extra stuff so that with each node you can associate whether it's the current node, whether it's been visited, what the tentative distance was, what the path was, right? And this can just be a string that you're building up or an array or something like that. And it's really not too bad to code up other than, you know, a horrifying amount of technical details, but nothing, you know, that you haven't already been doing for quite a while now. So it's really not bad. I might make this a 222 assignment. Come up with a implementation of this if I can find a cool way to do it. All right, so you want to try doing this on your own? I gotta come up with a good graph. No, I don't. I'll just come up with any graph. Come up with your own graphs. This way everybody does something different. Come up with a graph with, let's say 6 vertices, and you know, don't make it something like this. Make it interesting, throw some weights on. They have to be positive weights. Negative breaks the algorithm. And then try using Dijkstra's algorithm. But start off, go into your groups, find a spot on the board, and start off with a graph. And if I don't like it, I'll let you know.
It's similar.
That's good. Random weights. Yeah, sure. Give me a number.
Any numbers?
I looked them on
And make your graph big enough that you have space to like mark things and label things.
Yeah, I think that a little bit too. That a little bit too. Because now we're
We
gonna.
got the I-5 bridge in there.
0 is not a number.
I'm gonna do A0.
Is 0 a valid number?
I don't think so. I don't know, it might not break, but
I'm sorry, 7.
yeah.
And those are the 2 possible paths.
Okay, if we have more than six.
Yeah.
Okay, these are all the things.
Wait, where are we going? We're going 8. Yeah, where are we going? We're going 8F.
This is
Oh, yeah.
1. This is 1.
Okay, so from A we can go either to C or E. This is obviously the shorter one.
And so when you're relaxing vertices and stuff, it's easier if you put like one line through it instead of erasing it or something, so that you can go back and see what you did. So think about that.
So A is our.
Go in and get a different value.
You started at A.
Oh, yeah.
May I have a green or blue marker, please?
So do you have tentative distances?
Start at A.
We could add some, yeah.
Oh, yeah. Yes.
Well, at that point, we're just solving it, aren't
Max, there's nowhere else for us to go, though.
So you're either skipping steps or doing a lot of stuff in your head.
For this, yeah.
No, it's you'd have to like swap like.
I don't know. I'm finding it hard to do like a systematic. Yeah.
You swap these two around.
Hey, you look good.
It's like
What else can
yeah,
You've been trying to like all of it. Kind of need to be confusing.
I think you were doing the right thing.
It's too small and close. It's just getting confusing.
Okay. Yeah. That's what
So you've got here, if you go to 15, 10, 10, this 10, and you go to the shortest.
So you start off with A, relax 3 nodes, right? Because we have you got this 6, 9, and 3. Okay, so you got A is being done. Right. You don't put that in the again. So what's the next 3? Okay, so you're at 3. So there you go.
This is the one where you use your fantasy Elon Musk water boat and you go straight forward.
Yeah, that's also 3, I guess. Oh yeah. I didn't write one actually.
You're not done until you start. All you got is
All the numbers are put up in the cell.
And we
Yes.
from
Right.
Yes. Okay.
but now give us a half point
Because
6.
I thought we were starting.
That wasn't like this happened.
Give us
You don't want a bigger distance. So maximum means it's a smaller distance to data. Because you can already get there.
and then going to the
I just thought of writing it down.
but we don't have a choice.
So you always relax the
But you would add
How about we just write 3?
Yeah.
Cross out infinity and write 3.
shorter going Oh, the algorithm. Well, and
Eventually you'll just know what the shortest one is.
and the quickest,
Oh.
the quickest is yes, and then you find it going plus.
So 3 is our shortest.
You haven't visited E yet, right?
3 plus 2 should. Once we reach.
Base, right? Our current.
But if it's like 1, then.
And then we go with all of it.
Well, actually, it says smaller than the current.
Oh, yeah.
Which would be
If you don't circle a node, you're not done with a node until you've made that your current node and relaxed everything adjacent to
Then you
it.
can also go.
So you just did D, right? So you're done with D, and now you go back and you
Somehow,
find the
you're
closest
doing this
node.
randomly. And you get D from D.
You haven't visited yet, it looks like D.
Because you've got 9, 72, and 9.
It's because the way it's done and why it's right, but say we were going to this one.
This is our base, okay, then here we go.
You still go 1,
Go back?
No, this is
5, 6.
No, we can go back.
First you mark this node E as your current node.
F here, which would
And now you try to relax the algorithm. Yes, you say
be, we don't cross it out. If it's higher,
Oh, wow.
we only cross it out, which would be 7, which would be equal, so we don't cross it out.
The reason I like writing everything down is
If we go back to C, that'll also be higher. So D is a dead end.
I guess we say like we're done with it because every path is currently. Let's say we're done with it.
So normally when I give you the test, I give you like 10 or 12 numbers each time just to change.
No, see, so we have a current value of 7 to get to B. If we go this way, we still get there in 7. So this is done because all of the possible values are equal to or less than our current values.
Every number is 0. So down to here, which would be 8.
So we did this is all going.
Right.
Which is higher, even we don't want to do it.
7 plus 2 is 8. Could go down, it's not going to be 8. There's also one article that's passed.
But now,
That is correct.
relative to human.
We should probably mark in red. 8,
You can't have your output and like that.
Oh, no, we don't plan that corner.
Whoa, okay. I think that once you reach this point,
After you finish with a node,
well,
you look
6,
at
I
it.
mean, would get you
Once you get to a bigger scale, then it
you
becomes.
still have to evaluate this because it's the closest path. And if you, it's not going from C to K, but just from C to A.
Yeah.
They actually had to say one thing.
Okay.
Oh, it's landed something on Mars today.
Okay, so that's a 9.
Yeah, that was. One of my friends really like he's voicing Mars. And I'm thinking human, and I'm like, what? Okay, that'd be a big deal. Like, well,
Alright, fine. Okay, so you visited it here.
Does that produce the same? Does that produce 13 students?
Yes, because you get to be at 7.
Oh, yeah.
Equal.
Take that original mass.
So at each point, you find a node the shortest distance from the start. Right, that's
Wait, wouldn't it be greater or equal? They can
It's at a distance of 8.
we don't have.
Relax.
I just knew it. Previous one there.
And this would have been a 9,
Right,
so you don't
but-
relax that. Right,
So what we
9
do
is
is you go C to F,
8.
because F is the shortest path there.
So when
Yeah.
he thought
Then the shortest path is straight to D, the shortest
Like in this
path.
case, we took an equal path and it led us here.
No, every node
Oh,
you have
yeah.
visited.
therefore you were
Yeah.
I was like, I was even in my head like that. Yeah, that was throwing me off too. Like, do that. I'm like, oh, wait, that's the way you do it. Yeah.
So then you have, okay, we have.
so that probably not point
That one is gonna have to replace.
What are the results like?
Yeah. And then they,
Yeah, you go to here and then
average
they
time.
just do this smaller.
That's also a good question. How do they have something like this?
You
Whoa.
track average time, go through the speed limits, and then just.
They don't precisely know what the two possible ways to go here.
Even a green marker.
Well, no. So they just
Yeah, he's only.
Takes a while, there's this stop in the middle of the freeway. 9 and 14.
Yeah.
You
You walk out of the store and it's like.
Well, yeah.
They might not always.
He is like.
We'll get
Can you rate your shopping experience? It's like really. You know
whole Facebook will bring up ads for stuff that it hears you talk about, even if you're not in service when you're talking about it. Like, there's stuff that we've only ever talked about for like one time. I can narrow it to one time that we talked about something that wasn't in service. I've done it.
That's where I thought it was.
It's not hard.
But then you have to, and then if you keep
The algorithm still works technically. Can you set a path to have a length of 0? Is that possible?
Well,
No, it's a 0 path. Yeah, 0 would screw it up, I think.
Yeah, and
Like we make this 0 right here.
It uses all of
Well, that wouldn't matter because you go here, you have a 7. You go here, this is a 6. So there's no point. We go in here, that's a 9. No point because we can get there in 7. I guess 0 could.
I don't see why it would break the algorithm. I mean, other than the fact that you can't really distinguish these as different vertices.
The way is, yeah, they do the same vertices, you just have 0.
Yeah.
But you could just redraw it with one fewer vertex. So technically you could do 0, but practically it basically combines its vertices.
up to D for 6. From C to A for 2.
So we have to max everything from C first of all.
Yes.
Yeah.
So A goes.
There is cryptophones which you essentially have, right? So they're essentially where you have to.
So then if this was 2,
It's like
if it wasn't equal, when we went up here we get 8, which is less than that. So we say, oh, we can't go that way. And then we go back to E,
Well,
and
they
the next
also
lowest
don't
would
know
be B.
about the danger and the technical.
And then we could get to D in 8, which is
Remember when I well, I
Or
do
half
think
13.
they will be punished for it. I just don't
Yeah, we
think.
put over steps and boundaries.
Well, they sure do.
Yeah.
But the question is,
Would you add that?
Yeah,
I've never
but the
read
government should implement privacy policies. Okay, you can't require everything.
So there's a block here.
We have to open it back. It's all from that too.
Here we go.
So you're done with C.
Well, no, you don't need a conspiracy theories because
Which node is it?
before you tell me bribery is not legal again. My view
That's
is,
gonna be your new current node.
it's legal.
no, well, it's actually completely legal even if everyone knows about it. If you're patient, if you're willing to wait on that, then like, if you don't know,
That's illegal. That form of
Now our node. A.
Okay.
So that's painful.
Then I guess you'd say you're done with C. If you go to D, you find that this is 8, which is greater than, and you go to B, and you find that this is 9, which is greater than. You'd say that 7 is the shortest possible route to C, and then you're done with it? I don't know.
Alright.
AC is shorter than ADC. ADC is 8.
Yeah, basically AC is the shortest route to C, so if there's any other route there, it's going to be greater and not preferred. So we would say we're done with it because nothing else will go there.
Alright, so see if that gets you. So let's see, going from
4 days after. Yeah, we're just.
they
don't know. We got to the shortest.
It's like 7 minutes and 12. But usually that's us out 5 minutes early for some reason.
So you're right. So your relaxed one is here.
Then it's equal to AED BF. Because it is.
We went to F. This is no, we went to F so that we could see.
But there's 2. No, there's two. Both paths are valid.
It really
So
comes down
it'd
to
be
like
a-
cut off half your options twice from the start.
That you force yourself to go here.
And this is a absurdly low number.
But they were all random.
So your closest node goes to the connecting node. So your serving node, your relaxing node is basically D. The distance to E is actually two had a previous direction, then there would only be a way to go to. All of those zeros.
You would like saying that the whole process
Am I supposed to use mouse? Oh no, it broke. Thank you for doing
Okay, so now we're relaxed. Well, it takes 2 to get here. Another 3 will get us to E. So this will go plus 3 and we reach this with 5.
We're punching every node, we're testing every node, see if there's no, it's not.
We don't need to get to A. We can get to F, and this is a 2, 5, 7.
I know.
So part on it, part of F is
Yeah, we're not done yet.
almost.
Yeah, if we keep doing this, eventually we're going
You
to
don't
look at
get
this as the
brain
shortest
damage.
or relaxed.
You get all
Plus 1 is 5 will be better than 7.
all like hard.
But
You're
drop back to the very last step. But the important thing is
Go back
to
wrong.
just clean down.
But if you go back to
Wait
sleep,
on
most of those
And
things
then you're debating over here, because you need to add.
So you essentially there is actually
Yours is easy. Going from A to F.
Like, you know, it's like all.
Like, if B was 8, this is like systematic view, I guess. It's like you list your current and then the possible. You just look for the lowest value of F. So like if you always select the lowest, in this case it works. But from D, if this was 2 instead of 1, then you have B equals 8 and you go back to B equals 7.
How'd this come out? Okay, cool. Yeah, that makes sense.
Turns out when you make one of the roads for super, it's kind of hard to get.
That's true, yeah.
When you have like a bunch
Or
of.
assume that's just like I-5.
Okay, you got 5.5 minutes if you want. Change
I don't want
numbers
this
to
to
see
mess
what your like if you make this 400, right? What's it gonna come up with? So it doesn't use that. You just run through it and make sure there's other. This work out?
Yep. We got two paths that are equal to each other in length.
Okay, yeah, that can always happen too. That's a good example.
It's probably going well.
You follow around, they got you to there.
I haven't had a chance to work on it too myself.
Oh, I guess, yeah, so there's also this route.
Cool. So if you want, you got like 5 minutes, you could change this to like 6. And go back and see where that ends up being part of your first path. But it makes sense?
Yeah.
Okay, cool.
Maybe it's 6.
All right, so you're good to go if you're done and you're satisfied with that.
Wouldn't that just be the shortest path?
Yeah.
If I can figure out.
So we're starting from here, so relax the distances to really X A. And oh, so you're putting in the table. Okay, so okay, that should work. So E is an 8, D is a 2, D is 4, okay. So which node is closest now? It's like D. D is only 2, right? So D is closest node.
So, if
So we're not necessarily following a path here. We're just saying, okay, this is the next node that we're going to look at. So we're going to make D our current node. We're going to relax everything adjacent to D. What? D.
Oh, you guys
So
are
a
replying
D
to my text. Did you still need to do?
plus 2. Because it takes 2 to get to D. Alright, so now we can get to C in 12, which is better than infinity. C of 12.
How many do you remember?
How about D? That's 11. That's 11 plus 9. But we could already get to B in a distance of 4, right?
We have also an odd number.
We already had a path with distance 4, so we're not going to replace it with an 11. We're just going to leave it at 4. Right. All right, and then from B to F.
B to F is shorter than 9.
Right, it's 7 now. 5 plus 2, because it's 2 to D.
Right.
So that's shorter.
And E has specificity, then E would be 5.
That would be 5, right? Okay. I think you're good with that. So now we're going to find the closest node, looks like D. D, the distance of 4. So these are, so far, our best distances from A to each of these nodes. We have a way to get from A to B in 4. That's that. We can get from A to C in 10. That's that. And so on. So the closest node to A so far is going to be B. It's only 4.
So start at B.
Start at B, relax everything from there if you haven't visited. 6 plus 4, right, which is 10, which is better than 12, so that's good.
to D is 9 plus 4 is 13.
We've already visited D, so we don't have to adjust that. Right, you already visited D, so we're not gonna adjust the distances of that.
And then there's F, which is 1 plus 4 is 5.
Right. Okay, and so what's your closest node now?
My closest node now would be F,
Yeah,
and which is the target.
which is the target, so you're done and you can get there in a distance of 5.
I honestly do not understand yet.
Okay,
I don't understand enough to know what I'm doing.
even though you just did it.
And I just did.
Okay, try
Paradox.
try different versions of this. Try at least once writing this stuff on each vertex instead of in a table, because it may make it a little less confusing.
Okay.
Right, so if you actually write down a 10 here, right, and then you go over here at 10 plus 6 is 16, it might help, it might not. And then also writing down the actual vertices that you follow to get here, I think that will help more. So if you know a path to here, and then you're relaxing to this point, right, the path to here is whatever path you took to here plus the trip to D.
All right.
See if that works.
I have a question.
Yeah.
I know you said there was some restrictions on the graph that you can use, for example, to have you connect.
Mm-hmm.
So, like an example where you have this, and then you have like a little bit of going into a vertex.
Okay.
And one, and that's the shortest. Like keep going. Because of, so basically, the shortest path is still one.
Well, let's see, so if you start at A, right, and it's got a distance of 0, so we're relaxed, so this is a distance of 2 and 3. This would be a distance of 1, which is not better than 0, so we don't relax along there. And this becomes visited, so now we get that and we go from there. In practice, I think you can throw away loops, because I don't think they're ever going to help you.
Okay, I was worried something on the state.
Yeah, but I think even if you just follow the algorithm with loops in there, I think they get taken care of. What really trips it up is negative weights. And it's weird why that trips it up.
What are they? What are they?
Negative weight is like you gain time or you gain money by taking this road instead of having to pay a toll or sit in traffic. And that totally breaks the algorithm. It's really weird that that happens.
That wouldn't happen in like.
Yeah, it can.
It can.
Sure.
Oh, it can take back to you.
Yeah.
Not.
Or if yeah, I don't know when you go back in time, but it could be like a time machine road. Then you try 5.
Okay. I can normally talk about it.
Yeah, I think so, but I don't think